Quantum computing in climate modeling and environmental science. Welcome to the future of environmental innovation. Join us as we explore how quantum computing is transforming our understanding of climate change. Let's hand over to Lisa and Henry to continue.
Welcome to the deep dive. Today, we're diving headfirst into something really thought-provoking. What if, our future understanding of Earth's climate hinges on tech that sounds like pure science fiction? I mean, quantum computing. So our deep dive today, it's all about quantum computing on climate modeling and environmental science. We're going to explore how this cutting-edge stuff promises to, shake up how we understand and predict planetary changes.
Absolutely. And our mission for you is to really unpack why today's computers, even supercomputers, kind of struggle with just the immense complexity of Earth's systems. Then we'll look at where quantum computing might fit in, theoretically, and importantly, what's actually happening now, on the ground, and what's a realistic timeline. We'll pull out the key takeaways and maybe some surprising facts for you.
Okay, let's unpack this. That our sources keep calling current climate models beastly. Why? Why are they such a huge challenge, even for the best supercomputers we have?
Right, it's a massive challenge, and it's not just about speed. Not really. Think about it. These machines are trying to simulate the entire planet. Clouds swirling, deep ocean currents, ice sheets, everything.
Yes.
And the equations. They're incredibly complex, and, there are no real shortcuts. So what happens? Even the fastest supercomputers have to cut corners. They use these coarse grids. Imagine dividing the planet into big blocks instead of tiny squares. They simplify chemistry, make sort of good enough guesses for things like how clouds form.
Ah, okay, so it's not just needing more processing power, it's something more fundamental.
Exactly. It's deeper than that. The core issue, climate is chaotic, inherently chaotic. Research shows, tiny changes can ripple outwards hugely, like the difference between a hurricane forming or just a sunny day. That could literally depend on stuff happening at the molecular level. Trying to model even one cloud like that classically, you'd need to track, more particles than atoms on Earth. It leads to what we call an impossible number of calculations. It's not just slow. It's fundamentally beyond what classical machines can compute.
Wow, that butterfly effect thing really makes sense here. So if classical computers hit that wall, how does quantum computing break through? What's its, secret weapon?
Yeah, the secret weapon is that it's a fundamentally a different way of thinking about computation. Quantum computers use qubits. And these qubits, they can process a mind-boggling number of possibilities all at once because they can be 0, 1, or kind of both at the same time. That's superposition. It's weird but powerful. It lets them explore so many potential solutions simultaneously. And that just opens up amazing new pathways for climate modeling.
Okay, I think I get the concept.
Yeah.
But how does that translate? What specific improvements could we actually see in climate models?
Well, first, think finer grids, fewer shortcuts. Instead of simplifying, quantum computers could potentially model complex systems much more precisely, capturing those tiny microscale things that current models just gloss over.
Right, more detail.
Exactly. Second, better chemistry. Simulating atmospheric chemistry, pollutants, aerosols, greenhouse gases, it's messy. Quantum algorithms could simulate these molecular interactions directly, giving us a much, much clearer picture.
Okay.
And third, faster scenario testing. Imagine you want to test a new emissions policy or see what a big volcanic eruption does. Quantum computing could potentially run these what-if scenarios incredibly quickly, allowing scientists to test way more possibilities. And the key thing really isn't just doing current stuff faster, it's doing calculations that are completely impossible today.
Okay, the promise is huge. Definitely.
Mm-hmm.
But like you said, quantum computers are still small and noisy. They're not quite there yet. So what's the reality today? Is there actual progress or is it mostly just theory still?
No, there's definitely real momentum. Even with the hardware limits, we're seeing real advances in algorithm development.
Mm-hmm.
Scientists are actively designing quantum algorithms for weather, for fluid dynamics, chemical modeling, and we're even getting proof of concept results on the small quantum processors we have now. Yeah, and another exciting area is hybrid models. The idea is you use quantum computers for the really hard parts, like simulating specific molecules or these huge optimization problems, and then classical supercomputers handle the rest of the model. It's a clever way to use what we have.
Makes sense. Combining strengths.
Right. And it's not just academics working on this. Big players like NASA, the Department of Energy, national weather agencies, they're all investing. They're getting ready for when the hardware improves. So yeah, the groundwork is absolutely being laid right now.
And this isn't just about global climate predictions, is it? You mentioned environmental science more broadly. Where else could this tech make a difference?
Oh, definitely. It's fascinating how broad the applications could be beyond just the big climate models. Think about ecosystem modeling, simulating how a forest or an ocean ecosystem or ice sheets respond to changes. Quantum could give us unprecedented detail there. Then there's resource optimization, finding the absolute best way to allocate energy or water or land use. These are basically giant puzzles quantum might solve efficiently. And data analysis. We have so much environmental data now, satellites, sensors. Quantum machine learning might be able to sift through all that and spot patterns, correlations that we humans just completely miss.
Okay, let's get a bit more concrete. Can you give examples like what specific quantum algorithms are people looking at for this, and are there any actual early experiments happening?
Sure. So one type is quantum Monte Carlo. Classical Monte Carlo runs thousands of simulations to see what's likely to happen. Quantum versions might do that much faster or handle way more variables. Useful for uncertainty.
Okay.
Then quantum chemistry simulations is the big one. Modeling molecules in the air ozone, methane, AXA, those nitrogen oxides from pollution. It's super hard classically. But quantum algorithms like VQE, that's variational quantum eigensolver, sort of a quantum search for a molecule's stable state, or quantum phase estimation. They could potentially simulate these interactions with much higher accuracy.
Right, the chemistry part you mentioned earlier.
Exactly. And finally, optimization algorithms. Think about finding the best places to plant trees for carbon capture, or routing renewable energy efficiently. These are huge optimization puzzles. Quantum computers are theoretically really good at those.
And you said there are early experiments. Where are we seeing this in action, even if it's small scale?
Yeah, definitely early stages, but things are happening. IBM, for example, they've partnered with the Japanese Weather Agency, exploring potential uses, proofs of concept mostly, but still.
Okay.
Google has used its hardware for some small chemistry simulations. They keep publishing results, improving the techniques, and then lots of academic collaborations. MIT, Oxford, Zurich universities working together. They're trying to pinpoint exactly which parts of current climate models could get the biggest boost from quantum. And this work is starting to touch on some really big questions, like how will clouds behave as the world warms? That's a huge uncertainty now. Or what if the permafrost thaws? Modeling that methane release is tricky. Even designing better carbon capture materials, simulating new molecules for that. Quantum could potentially help there too.
It really does sound incredibly promising. Like it could unlock genuinely new insights, but there are always hurdles.
Yeah.
Right? What are the main roadblocks?
Oh, absolutely. There are some serious challenges,
Yeah.
no doubt about it. The biggest one is probably hardware limitations. Today's quantum computers, they just aren't big enough or stable enough yet for these huge climate simulations. Qubits are still noisy, prone to errors. Scaling up to millions of reliable qubits, that's a massive engineering challenge.
Yeah, I've heard about the error correction problem.
Exactly. Then there's algorithm development. A lot of the best quantum algorithms for climate, they're still kind of on the drawing board. Turning theory into practical working code for these machines, that's a huge task in itself. And finally, integration. Even when the hardware gets better, how do you plug these quantum machines into the existing incredibly complex climate modeling workflows? You can't just swap them in easily. That integration piece will take a lot of work. So yeah, most experts think we're still years away, maybe a decade, maybe more, before quantum truly outperforms classical computers on useful large-scale climate problems. Which leads to the question, what needs to happen to get there?
So bringing it back to our listener, why should you care about all this quantum computing and environmental science stuff? How does it affect you, potentially?
Well, the real-world value could be immense. Seriously. Think about getting more precise warnings for things like hurricanes, floods, wildfires. More lead time means communities can prepare better. Saves lives, saves resources.
Absolutely important.
And it means smarter policies. Policies based on models that can actually simulate local impacts of global changes, not just broad averages. And maybe most crucially, it could give us a much deeper understanding of those climate tipping points, those feedback loops and risks that our current models might not even see properly. It's about building a more resilient future, really. It's not just abstract science.
It really does feel like one of the most, exciting frontiers in environmental science, something worth keeping a close eye on. So we've covered a lot today, from why current climate models struggle to the really mind-bending potential of quantum computing and also the big challenges still ahead. It seems clear that, while the full impact might be years off, The groundwork is definitely being laid for what could be a revolution in understanding our planet.
Yeah. And maybe a final thought for you to consider. Think about the profound shift if we actually gain that ability to predict Earth complex behavior with, like, unprecedented certainty. What new responsibilities does that bring? What innovations? Maybe even ethical questions we haven't thought about. How could that deep understanding change how we live, how we plan for the future? Something to mull over.